All right, welcome to this lesson. This is an introduction to units and dimensions. Let's start out with a definition just so you get the basic idea of what is a dimension versus what is a unit. A dimension, you can think of it as an inherent property or an inherent measure of a quantity, and a unit is a way to assign a numerical value to that measurement. Okay, so I'll say it again. Dimension is the inherent measure. Unit is a way to assign a number. So let's make this super concrete with a couple of examples. Say the driving distance between St. Paul and Los Angeles is what you're interested in. Well, that's a length. How far? That's a length, okay? And length is a dimension. The length happens to be 1,930 kilometers or 1,200 miles. Kilometers and miles are different units to which we can assign a number to that length that we were interested in. As another example, the amount of mass in a given volume of water, that's called a density. Density is a dimension, okay? The density happens to be 1,000 kilograms per meter cubed, or 16.39 grams per cubic inch, okay? So grams per cubic inch and kilograms per meter cubed, those are examples of units. Those let us assign a number to the particular density that we were interested in. And just in case you're sort of rolling your eyes or groaning and saying, oh, I learned about units and dimensions in 8th grade or 11th grade or something, I want to assure you that possibly not by the end of this screencast, but by the end of this unit on units and dimensions, you are going to learn some fundamental, deep, useful, and new things about units and dimensions. Things that will surprise you that you probably have not seen before. Turns out there are 7 primary dimensions, okay? These are what we think of as being the fundamental dimensions of the universe. This is a little bit controversial. You might see different answers depending on exactly where you look, but we're going to say there's 7, and I've divided them into 3 groups where the groups are sort of a hierarchy of the frequency with which you'll see these dimensions used, at least in this class. So the most important ones for us are length, mass, and time. We symbolize these dimensions with L, M, and T, and then I've just given you some example units for each dimension over on the right here. In the second grouping, we have the amount of a substance, like how many oranges do you have, or how many molecules of carbon do you have, okay? Which we symbolize with N, and temperature, which we symbolize with theta. And again, there's some example units over here. You've heard of moles if you ever took chemistry. And then in this last group, we have electric current and luminous intensity, basically how bright is something. We'll encounter those less commonly, at least in this class. These are the primary dimensions. You should be able to recognize them and know their symbols, but they certainly don't cover all quantities in the universe. So there are other dimensions called derived dimensions. And these are formed as basically products and quotients, integer-powered products of the primary dimensions. And here are some examples. I'll run through them one by one, and I'll try to give you a little bit of intuition for each one. So for velocity, the dimensions are Lt to the minus 1, because velocity is or speed is like a distance per time. That's L divided by T. Acceleration is a change in velocity over time. So that gives us Lt to the minus 1 divided by time, which is Lt to the minus 2. Force's dimensions are mLt to the minus 2, and that's because force is like a mass times an acceleration. So we take the dimensions of acceleration and multiply them by m. Frequency has dimensions of t to the minus 1. You can think of that as meaning per time. Basically, how often does something happen? 3 times per week, 10 times per month, 5 times per year. Per year, that's dimensions time to the minus 1. Energy has dimensions ml squared t to the minus 2. That's because energy is sort of like work. Work is like force times displacement. If you don't know this from physics, that's quite all right. I'm just giving you an example. So force we know is mlt to the minus 2. If we multiply that by a displacement or a length, we get these dimensions here. Area has dimensions L squared. You can think of the area of a rectangle as length times width. That's the product of 2 distances, 2 lengths. Volume is like length times width times height, so the dimensions are L cubed. And density is mass per volume. That's m divided by L cubed, or ml to the minus 3. The notation we use for dimensions is that to talk about a certain quantity's dimensions, we put it in square brackets. So when we write square brackets around acceleration, it means what are the dimensions of acceleration? An acceleration is a change in velocity. It's velocity divided by time. So that's L divided by T, which is LT to the minus 2, just like on the last slide. We could ask, what are the dimensions of debt to GDP ratio? Now, debt is an economic quantity. It's a measurement of, it's how many dollars. Dollars is an amount of substance. So the dimensions of debt are N. GDP is gross domestic product. That's an amount of money per year. So the dimensions are N divided by T. The ratio of those things is N divided by T. That has dimensions of T. So debt to GDP ratio has dimensions of time. One other important thing to note is that some quantities are dimensionless. And the way we write that is that they have dimension 1. That's how I'll write it. And that's because usually we're dividing two things that have the same dimension, and the dimensions cancel out to give us something dimensionless. So like take the number pi that you know. Pi is the ratio of a circle's circumference c to its diameter d. So if we ask what are the dimensions of pi, well, it's the dimensions of circumference divided by diameter. But circumference is a length, and diameter is a length, so length divided by length gives you dimensions 1. So we say that pi is a dimensionless number. As a second example, albedo is the ratio of reflected radiation from a surface to the incident radiation hitting it, right? So it's a ratio of radiation to radiation. We haven't even said what the dimensions of radiation or radiation energy are, but it doesn't matter. We're taking the ratio of two things that have the same dimensions, so it has to be a dimensionless quantity. The dimensions of albedo are unity, dimensionless. Now, let's talk about units. Any given dimension, whether it's a primary or a derived dimension, may be measured in various units. So I won't read all of these out loud, but lots of ways to measure length. Feet, miles, light years. Area can be measured in acres or hectares. Velocity can be measured in miles per hour or meters per second, and so on. So any given dimension, there's lots of different unit systems that you might be able to use. So we've reached the end of this lesson. I want you to ask yourself if you can do the following things. Can you explain the difference between units and dimensions? Can you state the 7 primary dimensions, and especially the first 5 that were in our list? Can you recognize and calculate common derived dimensions? Can you identify dimensionless quantities? And can you recognize if units are units that are describing the same dimensions? So that's it for now. Thanks very much.